Analysis of continuous fiber composites. As we know, composites are materials where two components have been added, intentionally added. One is the matrix and another is the fiber. The fiber is added for reinforcement purpose, whereas the matrix does the role of holding the fibers together. There are several types of fiber reinforced composites, and out of many types, one is called unidirectional continuous fibers composites. Unidirectional continuous fibers provide the maximum reinforcement to the composites. It is known that the continuous fiber composites provide the maximum strengthening or reinforcement to the matrix. Although manufacturing of a continuous fiber composite is cumbersome and expensive when compared with short fiber or particulate composites, the best strengthening and stiffness can be obtained by continuous fiber composites. That means the fibers are put in the direction of the maximum tensile load in that component. This ensures that entire of the tensile load is taken by the fiber along its longitudinal direction. Therefore, it is important to see how we can calculate the modulus and strength of a continuous fiber composite in its longitudinal direction. Let us consider this composite, which has all of its fibers arranged in one direction and the fibers are continuous. So in this composite, we can see that fibers are all aligned in one direction. They are parallel to each other. There is no fiber in any other direction but one direction, and this direction is called longitudinal direction. That means along the length side. Now with this idealized composite, we have fibers. This blue color is the fiber and the white color is matrix. We will represent fiber as F and matrix as M. L is the length of this composite, the initial length of the composite. Now imagine we are applying a tensile load of Fc to this composite. So Fc on this direction and Fc on this direction. So this is the load. Because of this load, this composite will extend by delta L. So delta L is the extension. So after extension, we get the composite in this form. It is still in the elastic range. So that means if we release the load, it will go back to this length. So in this situation, the strain will be given as delta L over L. Now we will conduct the analysis for this type of composite in its longitudinal direction, that means in this direction. We will try to find out the modulus and strength. Now let us do this analysis. So equilibrium of the forces. So we will do the analysis of the forces. Now Fc is the force on the composite. So whatever force we are applying on the composite is being shared between the fiber and the matrix. F indicates fiber, M indicates matrix. So this force will be a sum of force taken by the fiber and force taken by the matrix. Now we know the force can be written in the form of stress multiplied by cross-sectional area. So Fc, which is the force on the composite, can be written as sigma c multiplied by AC. Sigma c is the stress on the composite, overall stress, and AC is the overall cross-section area of this composite, complete cross-section of this composite. It will be equal to the stress in the fiber, sigma F, multiplied by the cross-sectional area of the fiber. So we have, these are the fibers, these blue color. So the cross-sectional area of these fibers, if we sum them together, that is AF. And sigma F is the stress in the fiber, in each of the fibers. So we assume that all the fibers are loaded in the same manner. Therefore, stress will be the same. Plus sigma M AM, which is for the matrix. So stress in the matrix multiplied by the cross-sectional area of the matrix here. Now, geometry of deformation. So total strain in the composite will be the same as in the fibers or the matrix. Now, since this material is one single material, the deformation will be together. That means the fiber and the matrix will deform equally in the same manner. So therefore, we can say that strain in the composite is equal to strain in the fiber which is equal to strain in the matrix. So strains will be same in the overall the composite, in the fibers as well as matrix. So this is our geometrical conditions. So the stress-strain relationship will be given as this. So sigma c, which is stress in the composite, is equal to the modulus of the composite, strain in the composite. Similarly, we can write sigma f is equal to EF, which is modulus of the fiber and strain in the fiber. Stress in the matrix will be given as modulus of the matrix and strain in the matrix. Combining equation 4.2b and 4.4 and applying F is equal to sigma A. Well, we have already applied F equal to sigma A to obtain 4.2b. So basically we are going to substitute for stress from these equations from 4.4 to 4.2. That gives us modulus of the composite multiplied by strain in the composite. So this is the stress part, stress sigma c multiplied by the cross-sectional area of the composite is equal to EF epsilon f AF. So this is for the fiber and this for the matrix. So equation 4.2b has been modified in this way. Now using 4.3 we can write, whereas 4.3 equation has given us this one. Strain in the composite is equal to strain in the fiber is equal to strain in the matrix. So that means epsilon c, epsilon f and epsilon m, they are all equal to each other. So basically they will get cancelled out. So we will obtain EC, which is the modulus of the composite, is equal to modulus of the fiber multiplied by this area ratio. Area of the fiber divided by area of the composite. And then modulus of the matrix, area of the matrix divided by area of the composite. So this is the area ratio and this is also the area ratio. Now, if the fibers extend to the full length of the composite, then the area ratio will be same as the volume ratio, which has been proven here. So area ratio, for example, AF over AC is equal to AF over AC, and we multiply length on both sides, numerator and denominator. So now area of the fiber multiplied by the length is same for the fiber and the composite. So this will become volume of the fiber. Similarly, this will be volume of the composite. So volume of the fiber divided by volume of the composite will be given as volume fraction of the fiber, VF. Therefore, this ratio can be written as volume fraction of the fiber, and this ratio can be written as volume fraction of the matrix. So now we have a relation which gives the modulus of the composite as equal to EF VF plus EM VM. That means modulus of the fiber multiplied by the volume fraction of the fiber plus modulus of the matrix multiplied by the volume fraction of the matrix. So equation 4.7 is also known as the rule of mixture. So this is known as the rule of mixture. Similar relations can also be written to determine strength, Poisson's ratio, thermal conductivity, etc. in the fiber direction. So that means if we replace EC by other properties like strength or Poisson's ratio, then we can obtain the similar kind of rule of mixture. So this is the equation for modulus of a composite in the longitudinal direction for a unidirectional continuous fiber composite. Now, similar to the analysis we did for modulus, we can do another analysis for the strength of the composite in longitudinal direction for unidirectional continuous fiber composite. So we can write equation 4.2b in the form of force. So we have seen that equation, stress multiplied by the cross-sectional area for the composite is equal to stress in the fiber multiplied by the cross-sectional area of the fiber plus stress in the matrix multiplied by the cross-sectional area of the matrix. So this equates to force. So dividing both sides by cross-sectional area of the composite, we obtained sigma c, which is the stress in the composite, is equal to stress in the fiber multiplied by this area ratio and plus stress in the matrix multiplied by this area ratio. So just like we did before, the surface area ratios, surface area ratios can be replaced with volume ratios for longitudinal fiber composites. So we can write sigma C is equal to sigma F VF plus sigma M VM. VF is the volume fraction of the fiber and VM is the volume fraction of the matrix. So this equation can give us the strength of the composite if we are using the ultimate fracture strength of the fiber and ultimate strength of the matrix. Now for calculating the ultimate tensile strength of the composite, we replace the stresses to the maximum possible stress, which is the ultimate tensile strength of the composite, the fiber and the matrix. Thus we can write sigma Cu, which is the strength of the composite, ultimate tensile strength of the composite, is equal to the ultimate tensile strength of the fiber multiplied by the volume fraction of the fiber plus ultimate tensile strength of the matrix sigma mu multiplied by the volume fraction of the matrix. Now this is one equation we can use to find out the ultimate tensile strength of the composite if we know the properties of the fiber and the matrix. Now in this equation we are using sigma mu as the ultimate tensile strength of the matrix. So we will do some modification of sigma mu in this equation to find out a better equation for sigma Cu. Let us first consider unidirectional fiber composite. Let us also see bidirectional fiber composite and random fiber composites. And here we will see schematic stress strain behavior of the fiber, the matrix and the composites in different fiber orientation arrangements. So if we plot the stress strain curve for fiber, then this will be something like this. Most of the fibers that we use for composites are brittle in nature, that means they will fracture in brittle manner. And this is the matrix. So matrix has got much lower modulus and much lower strength compared to the fiber. If you are going for unidirectional fiber, then for 0 degree orientation, that means the fibers are oriented in the longitudinal direction and we are applying stress in the same longitudinal direction. So this we call it 0. Then in this case we will achieve a very high strength of this composite. If we change the direction, fiber direction to 90 degree and we are applying the load in 0 degree, this direction longitudinal, then we will find that the strength of the composite is not much. It is very close to that of matrix. So that means there is hardly any strengthening effect. For any other direction, the values will be in between these two. So for 45 degree, we may obtain this one. So this is for unidirectional fiber. For bidirectional fiber, that means the fibers are oriented in two directions. In that case, for 0 degree, we can achieve a high strength here. For 90 degree, that means in this direction also we can achieve very similar, very close value of the composite because the fibers are oriented in both directions. So whether we apply force in this way or this way, it doesn't make very big difference. For 45 degree, we will have some reduction. If we have a random fiber orientation, so in that case 0 degree, 45 degree and 90 degree orientation of loading will not change much and it will give a more or less a very constant value. So this is the schematic diagram or typical understanding of how composites behave. Now you can see that when the fiber is going to fracture, that means we are applying the maximum stress in a composite. So fiber will break when the strain is here at this point in this case. Therefore in any composite, failure will happen when the fiber actually fracture, and fibers will fracture at a much lower strain than the matrix because the matrix can sustain much larger strain than fiber. The stress value of the matrix should not be the ultimate tensile strength of the matrix, but rather the stress at the strain at which fibers fracture. So we assume that the composite actually fails once the fibers have fractured. So therefore, we will replace the ultimate tensile strength of matrix by a much lower value of the stress, which will be the stress at the strain at which fibers fail. For example, if this fiber fails at this strain, so corresponding to this strain, we can find out the stress value on the matrix, and we will use this. Since at the point of fracture of brittle fibers, the composite will fail, which means that the matrix will be stressed only up to the fracture strain of the fiber. Hence, sigma mu, which is the ultimate tensile strength of the matrix, should be replaced by sigma m dash, which is the stress at the in the matrix at the strain equal to the fracture strain of the fibers. So this replacement we will do, and we will modify the equation. Sigma cu, which is the strength of the composite, equal to sigma fu, ultimate tensile strength of the fiber, multiplied by the volume fraction of the fiber, plus sigma m dash, which is the stress at the strain when the fiber fractures, multiplied by Vm, which is the volume fraction of the matrix. So this equation gives a lower value of the strength of the composite, but this is more realistic because we are using correct value of the stress here rather than using the ultimate tensile strength of the matrix. Now, it is found that the rule of mixture for strength calculation is only applicable if the volume fraction of the fiber is above a critical value, which means that the strength calculation will be incorrect if the volume fraction of the fiber is below a critical value. So let us try to understand what is this critical value of volume fraction. Now, from the rule of mixture which we have developed just now, this is the equation. Here sigma cu is equal to sigma fu, volume fraction of fiber, plus sigma m dash 1 minus Vf. So this is the volume fraction of the matrix. For Vf equal to 1, this part will be 0, and this will be the maximum value, which is sigma fu. Sigma fu is the ultimate tensile strength of the fiber. So this will give us this point. Now when Vf is 0, sigma fu, this part will be 0, and this will be the value equal to sigma m dash. So this will be given here because volume fraction of fiber is 0 here. So if we connect these two extreme values of the composite strength, we can see that there is a straight line relationship, there is a linear relationship. This straight line shows the rule of mixture. Now, when volume fraction of fiber is 0 or very close to 0, the rule of mixture predicts the strength of the composite as sigma m dash. But we know that for 0 volume fraction of fiber, the strength of the matrix, that means 100% matrix, strength of matrix is higher, sigma mu, which is the ultimate tensile strength of the matrix. That means for lower percentage of fiber on the lower side, which is close to 0, the composite has lower strength than the pure matrix. For a hypothetical case of all load supported by the matrix, if there is no fiber, Vf is 0, then of course the maximum strength is the strength of the matrix, sigma mu. For when the volume fraction of fiber is 1, that means no load is being carried by the matrix. In that case, the load supported by the matrix will be 0 here. So if we connect these 2 points, then we get a straight line. Now, these 2 straight lines will cross here at this point, and this is known as V critical, or volume fraction of the fiber critical. So that means if the volume fraction of fiber is higher than this value, then we may achieve some strengthening. Below this, there will be no strengthening because the matrix is stronger compared to the composite. In order to find out V critical, because since at this point both lines cross each other, so this line has got equation of this one, and this rule of mixture line has got equation of this one. So we will equate these two, the right hand side of these two equations, which has been done here. So this critical value is defined by the following formula. So this one comes from here, and we have replaced Vf by V critical, and the right hand side of here comes from this one. So by using equation 4.13 we can find out the V critical value for the composite. Now from figure 3.5, which is this figure, it is seen that the effect of strengthening is effective only above V1. Now, since the matrix can give us maximum tensile strength of sigma mu here, that means even beyond V critical, we still do not achieve the maximum strength until we reach this point. Because until this point, we can achieve the maximum strength just by the matrix. We do not have to add any fiber in it. So therefore, we draw a straight line here, a horizontal line here, and we take the values V1. Now, any composite which has got volume percentage of fiber more than V1, we can achieve strengthening. Below V1, actually we are not gaining any strengthening, because the matrix is able to give us higher value of the ultimate tensile strength. So in order to find V1, we can use this equation, and here we replace sigma Cu by sigma Mu, because this is the maximum strength of this composite. So sigma Mu is equal to sigma Fu V1 plus sigma M dash 1 minus V1. Solving this equation, we can find out V1 equal to sigma Mu minus sigma M dash over sigma Fu minus sigma M dash. So using this equation, we can find out the value of V1. That means the fiber percentage, the fiber fraction beyond which we can achieve some strengthening in a composite. So we should be able to find out V critical, V1, and also the strength of the composite using this equation. It has been observed that the maximum volume percentage of fiber can be achieved up to 0.8 when we get good strengthening, and the actual strength of any composite is about 65% of the theoretical value. And this is because of many defects in manufacturing, because the manufacturing can introduce many defects, and therefore we can never achieve the theoretical value of the strength. So these things we should keep in mind. And the volume percentage of fiber in unidirectional fiber composite can be in the range from V1 to 0.8. Finally, I would like to summarize. Best reinforcement for a composite can be achieved in unidirectional continuous fiber composite. Both modulus and strength of a unidirectional fiber composite in the longitudinal direction can be predicted by the rule of mixture. There is a critical fiber volume fraction below which fibers do not provide any reinforcement to the matrix. Thanks for watching. If you have any comment or question, please write them down below in the comment section.